The focus of this video will be type 1 error and type 2 error. To understand type 1 and type 2 error, we must also review hypotheses and the normal distribution curve. We'll start by reviewing hypotheses. When a researcher has a hypothesis, it is known as a research hypothesis, and it is sometimes called an alternative hypothesis. A hypothesis is an expected answer to a research question. It's usually written as a statement. The null hypothesis is a statement contradicting or refuting a research hypothesis. Therefore, whenever we set up a research hypothesis, a corresponding null hypothesis is implied. Let's take a look at an example of a hypothesis. We use capital H subscript 1 to stand for the first hypothesis. Our hypothesis can be, people who meditate will have lower stress than people who do not meditate. The null hypothesis is a contradiction to this. So the null hypothesis would state that people who meditate will have higher or equal stress to people who do not meditate. The reason the null hypothesis will say this is because either of those statements make the research hypothesis incorrect. So to summarize, a research hypothesis is our statement done by researchers about what is expected to be true, and a null hypothesis is generated from that as a contradiction to the research hypothesis. A null hypothesis is presumed to be true until the researcher has enough evidence to reject the null. Let's take a moment to differentiate between a directional hypothesis and a non-directional hypothesis. The names tell you what the difference is. A directional hypothesis is one in which the direction of the result is stated. For example, if I'm comparing two groups, let's call them group 1 and group 2, and I hypothesize that the mean of group 1 will be higher than the mean of group 2, I'm positing the direction, that 1 will be higher and group 2 will be lower. It's also a directional hypothesis if I hypothesize that the mean of group 1 will be lower than the mean of group 2, because here I'm saying group 1 will be lower and group 2 will be higher. In contrast, a non-directional hypothesis will simply say that something will be found or that groups will be different. For example, if I hypothesize that group 1 and group 2 will have different means, I'm not indicating the direction of those differences. That is, I'm saying that 1 will have either a higher or lower mean than 2, but I'm not telling you which of those two directions I expect it to go. Let's apply this to our hypothesis about meditation. If we hypothesize that those who meditate will have lower stress than those who do not, we've indicated the direction, that group 1, the meditators, will be lower than group 2, the non-meditators. Whenever we have a directional hypothesis like this, the statement that the groups will be equivalent or in the opposite direction both go to the null. If we have a non-directional hypothesis, for example, if I had said that those who meditate will have different levels of stress than those who do not, then only the statement that the two groups will be equal goes to the null. Let's try this out with three hypotheses. Hypothesis 1 states that babies and children will sleep different amounts on average. Hypothesis 2 states that those who exercise will have greater mean life satisfaction than those who do not. And hypothesis 3 states that unemployed persons will spend fewer mean hours driving per week than employed persons. Pause here and indicate whether each of these is directional or non-directional. The first one is non-directional because we're only stating that the two groups will be different, but we're not stating which group will have higher or lower average amounts of sleep. The second one is directional because we specify which group will have the greater mean than the other group. Hypothesis 3 is also directional because we state that there will be fewer hours in one group. Therefore, in the first one, we're only saying that the means will be different, but in the second and third hypothesis, we're specifically telling the direction of the difference. That is, we're indicating which of the groups will have the higher mean score. Let's pause again to figure out what the corresponding null hypotheses are. Try them yourself, then hit play to see the answers. Remember, the null hypothesis is anything that goes in opposition to the research hypotheses. The null hypothesis can be written with the symbols capital H subscript 0 for the hypothesis of nothingness, or the hypothesis that there is nothing to find. So our first null would be babies and children will not sleep different amounts on average. That not is the contradiction to our research hypothesis. The corresponding null for our second hypothesis is that those who exercise will have lower or equal mean life satisfaction compared to those who do not exercise. Because our hypothesis specified greater, our corresponding null needs to focus on things being lower, and the null always gets a statement of equivalence. Now let's look at the null for our third hypothesis. Unemployed persons will spend more mean hours or the same mean hours driving per week compared to employed persons. Notice that in all three null hypotheses, the null gets a statement of the groups being equal, but when we had directional hypotheses, like where we said greater or fewer, the null hypothesis also had the counter of lower or more, respectively. Once a hypothesis has been generated, it can be tested to see if it is supported or refuted. Notice here that I'm using the words supported or refuted rather than proven or disproven. In behavioral sciences, such as psychology and sociology, we're oftentimes testing to see if our hypothesis has enough evidence for us to strongly believe it, rather than to prove it without a doubt. The reason for this is because we set something called a confidence interval. That means we're going to be using a threshold that doesn't give us certainty, but does give us some kind of cutoff where we say the evidence is pretty strong here, so we're fairly confident that the hypothesis is or is not correct. When our results are strong enough to support a hypothesis, they are considered statistically significant. Statistical significance does not mean meaningful. Instead, statistical significance is a determination that the evidence to support the hypothesis is strong enough for us to have high confidence that the hypothesis is indeed true. Remember, statistical significance does not guarantee that your result is useful or meaningful, and it does not guarantee that your hypothesis is correct. Two key things are used to improve our likelihood of having a statistically significant result if in fact our hypothesis is true. If you have a large effect or a large result, you're more likely to be able to detect that your hypothesis is likely true. If you have a large sample size, this also increases your ability to find support for your hypothesis if your hypothesis is true. Once we have generated our hypothesis and collected our data, we then assess our evidence and draw a conclusion about our hypothesis. Ideally, our conclusions will have no error. If I hypothesize that something is true, and in actuality it is true, then I'm hoping to find that. If I hypothesize that something is true, and in fact it is not true, then I'm hoping my evidence will show me that it is not true. In these two scenarios, I would have no error. Let's think back to our hypothesis about meditation and stress. If I hypothesize that those who meditate will have lower stress than those who do not, and this is actually true, then I'm hoping my evidence will show that I was correct. However, if my hypothesis is not true, then our hope is that our evidence will show us that. That is, we don't care so much as researchers about whether or not our hypothesis is supported or refuted. The bigger concern for us is whether or not our conclusion is correct. If I conclude that my hypothesis was correct, when it was actually correct in the population, then I have no error in my conclusion. In addition, if I conclude that my hypothesis was incorrect, when in fact it was incorrect in the population, then again I have no error in my conclusion. It is okay to have a hypothesis that is refuted. The bigger concern here is missing truth, that is, having a wrong conclusion. We want our conclusion to match reality. This brings us to the two kinds of error that can occur. A type 1 error occurs when we conclude that our hypothesis was correct, when in reality, in the population, our hypothesis was actually incorrect. This can just happen randomly when we collect data sometimes. That is, if something is not true in the population and I gather a sample from the population, I might end up with evidence that suggests my hypothesis was true. If this is so, I will likely conclude that my hypothesis was true, and I will not know that I've made an error. A type 1 error is a big concern for us in research. Again, type 1 error is when we conclude that our hypothesis was correct, when in fact it was incorrect. Typically, in the behavioral sciences, when we state that our hypothesis was significantly supported, what we actually mean is that we are 95% sure that our hypothesis was correct and that we are not making a type 1 error. The second type of error that can occur is called a type 2 error. You'll notice by the name of it that it's secondary in its focus. That means we're more concerned with making sure we don't make a type 1 error than we are concerned with making a type 2 error. Statisticians are more careful to avoid making a type 1 error and are more accepting of making a type 2 error. Let's take a look at what a type 2 error means. We've made a type 2 error if our hypothesis was actually correct and we concluded that it was incorrect. This can also happen sometimes. My hypothesis could be correct, but when I randomly gather data from the population, I might end up with data that refute my hypothesis. Then based on those evidence, I would conclude that my hypothesis was wrong. But if in fact my hypothesis was right all along and my evidence just somehow missed this, which can occur randomly, then I am making a type 2 error. Type 1 error and type 2 error are connected to the null hypothesis. Whenever we posit a research hypothesis, keep in mind that a corresponding null hypothesis is also posited. The null hypothesis is always a statement contradicting our hypothesis. Because of this, we can think of the type 1 error as rejecting the null when we should have retained the null. And a type 2 error is when we've accepted the null when we should have rejected the null. Let's put this into context with an example. Let's presume that I have a hypothesis about height related to the biological sexes of male and female. If I hypothesize that males are taller than females, then the null hypothesis will say that males are shorter or equal in height to females. Now presume that in reality it is true that males are taller than females. Then my hypothesis is correct. If I collect evidence and it shows me that males on average are taller than females, I'm going to retain my hypothesis and reject the null. That means I'm going to conclude that I was right and that males are taller than females, and my conclusion matches that of reality outside of my data set. In this instance, there is no error. But let's say that my evidence showed that males were taller than females, but in reality outside of my data set, this is not true, and in fact males and females are the same height on average. If my evidence showed that my hypothesis was correct and that males are taller than females on average, and thus I reject the null when the null was actually correct, then I have made a type 1 error. Let's talk about the same example in looking at type 2 error. Let's presume that my hypothesis is still that males are taller than females on average. Again, let's presume that this is actually true outside of our data set, that reality is that males are taller than females. If I collect data and my data show that males and females are of equal height on average, I'm going to conclude that my hypothesis was wrong, and I will accept the null hypothesis. However, my evidence is suggesting to me that my hypothesis is not correct, when in actuality outside of my data set, unbeknownst to me, my hypothesis was right all along. In this instance, I'll have made a type 2 error. I will have rejected my correct research hypothesis and retained the incorrect null hypothesis, when in fact my hypothesis was right all along, but my evidence, due to random chance, did not provide me the support I was looking for to draw that correct conclusion. Notice that I've been using the word likelihood, and likelihood is all about probability. This is because behavioral scientists use what's called a confidence level to determine whether the result is significant. Typically, we need to be at least 95% sure that our hypothesis is correct before we're able to conclude that our results are statistically significant, and thus we can support our hypothesis and reject the null. When we say we are 95% sure of our result, we are also saying that we are 5% unsure. Another way of thinking about this is if I say I'm 95% sure that my hypothesis is correct, I'm saying I'm 95% sure I'm not making a type 1 error. That also leaves open up to 5% chance that I'm wrong. So whenever I say I'm 95% sure that my hypothesis is correct, I'm also saying there's a 5% chance that I'm making a type 1 error. The chance of a type 1 error is called a p-value. And as behavioral scientists, we want to have our p-value set at less than 5%. That means we want to have less than a 5% chance of making a type 1 error. This p-value is sometimes also referred to as a significance level. We spent a lot of time here just talking about different hypotheses in scenarios, but we haven't tied this back to what it means in statistics. That is, we haven't looked at it with graphs or numbers yet. So let's pull the two concepts together. When we say we're 95% sure of our result, or thus that our result is statistically significant, we're actually referring to a use of the normal curve. Let's briefly review some important aspects of the normal curve to get us ready for understanding statistical significance and hypothesis testing. When we draw the normal curve, the mean is at the middle, and scores become less likely as we move out from the mean. We chart those movements using standard deviations or z-scores. Standard deviation can be thought of as error in the mean. The mean tells us where scores tend to fall on a variable, but the standard deviation says, let's not believe that all the scores are exactly at the mean, because that's not true. The scores are somewhere around that mean. So the larger the standard deviation, the more spread out scores are around the mean. The smaller the standard deviation, the closer together scores are to the mean. Let's take a look at this with an example. We'll use stress here. Presume I have a sample of adults whose stress score on a scale of 1 to 10 on average was 6.00, and by the average here I'm referring to the mean. Let's say that the standard deviation for stress in that sample was a 0.5. We can use this mean and standard deviation to fill in the raw scores that correspond to each of the z-scores under the normal curve. Now I have raw scores going from 4.5 at a z of -3 up to 7.5 when z is equal to 3. You might recall from other study materials that 95% of the scores are expected to be from 1.96 standard deviations below the mean to 1.96 standard deviations above the mean. That means we expect about 95% of the scores to be between approximately a raw score of 5 and a raw score of 7. Another way of thinking about this is that if the normal curve is true and 95% of the folks are from a z-score of -1.96 to a z-score of 1.96, then if I grab any person at random from this sample, I have a 95% chance that they have a z-score from -1.96 to +1.96. So I'm 95% sure that any randomly selected person will be from within this z-score range. This knowledge is the foundation for how we set up statistical significance. When we determine statistical significance, we use this same concept, but we adjust it by sample size. The larger your sample size, the more accurate your mean is likely to be to that of the population mean. Remember that samples in statistics are used to generate an understanding about what's likely true of populations. Samples are subsets of populations, so we don't expect them to be identical to the population. But the larger our sample, the less impact an outlier can have, and thus the more accurate our sample mean is at reflecting what's true of the population mean. Therefore, means from samples are used to get a snapshot of what's likely true in the population, but we keep in mind that the sample mean is likely to be a little bit incorrect. The standard deviation tells me that there's variation out there. 95% confidence intervals refer to the numbers within which we are 95% sure the actual population mean exists. Our confidence intervals take into account sample size. Here's the formula we use to find our confidence intervals. Our 95% confidence interval is equal to the mean plus 1.96 times the standard error to the mean minus 1.96 times the standard error. Standard error is an adjusted version of the standard deviation which takes into account the sample size. So standard error is equal to standard deviation divided by the square root of n. When we fill this in, we find the range around the sample mean, where we're 95% sure that the actual population mean exists. Let's try that with the data we have here. When we do so, we get that our confidence intervals will be equal to the mean plus 1.96 times 0.5 divided by the root of 100 to the mean minus 1.96 times 0.50 divided by the root of 100. Therefore, our confidence interval ranges from 5.902 to 6.098. Therefore, we believe that the true population mean is somewhere between 5.902 and 6.098. Even though our sample mean is at 6, we presume there to be at least a little bit of error in our sample mean, and we use our standard deviation, adjusted by our sample size, to get the range around the mean where we're fairly confident the real population mean exists. Therefore, presuming that the data were collected randomly, we're about 95% sure that the actual population mean for stress is between 5.902 and 6.098. Take a moment here to test your knowledge using the data from 3 different variables. For variable 1, we had a mean of 20, standard deviation of 12, and sample size of 9. For variable 2, a mean of 10, standard deviation of 1, and sample size of 100. And for variable 3, mean of 55, standard deviation of 4.5, and sample size of 400. Use these to solve for the confidence interval using the formula. Confidence interval is equal to the mean plus or minus 1.96 times standard deviation, which has been divided by the square root of the sample size. For the first one, we need to start by square rooting the 9 to get a 3, then divide the 12 by the 3, which gives us 4. If we carry out our steps, we'll get that the confidence interval for variable 1 ranges from 12.16 to 27.84. Let's try it again with variable 2. We fill in our mean, standard deviation, and sample size, and carry out the steps the same way. Remember to use proper order of operations. When we do so, we get that the confidence interval is from 9.804 to 10.196. We repeat the same process for variable 3, and we get that the confidence interval is from 54.559 to 55.441. Notice that when the standard deviations were larger and the sample sizes were smaller, such as in variable 1, the confidence interval is quite large. But when the standard deviation was small and the sample size was large, like in variable 2, the confidence interval is rather narrow. We can use the information we have here to create the normal distribution curve for each of these variables one by one. We'll start by filling in the mean and using the standard deviation to find the raw scores that correspond to the z-scores. Next, we can plot a line for each of the two ends of our confidence interval. So I'm going to place a line from 12.16 up to the curve and from 27.84 up till it hits the curve. So though my sample mean is at 20, I believe that the real population mean is somewhere between a 12.16 and a 27.84. This is where I'm 95% confident the real mean is. I'll do the same thing by sketching a graph for variable 2 and filling in my 95% confidence interval, and I'll also do my sketch for variable 3, finishing off by filling in the confidence interval. Here, the visual comparison is pretty clear that variable 1 has the widest confidence interval, and variables 2 and 3 have comparatively smaller confidence intervals. Notice that variables 2 and 3 both have fairly large sample sizes compared to variable 1, and they both have smaller standard deviations than variable 1. Now we're ready to put it all together to understand how confidence intervals and the normal curve are used to test hypotheses. Let's presume that I wanted to know whether those who meditate had lower stress than those who do not meditate. I'd have to collect data from persons who meditate and from a sample of persons who do not meditate. From that, I would need to generate their means and standard deviations, and then use those to find the confidence intervals. Let's presume that we collected these data, and for the meditation group, we found a mean stress score of 4, a standard deviation of 2, and a sample size of 16, and that for the non-meditation group, we had a mean score of 6, standard deviation of 2, and sample size of 16. Let's find our confidence intervals. When I do this for the meditation group, I get that my confidence interval ranges from 3.02 to 4.98. So this means I'm about 95% sure that the actual population mean is going to be from 3.02 to 4.98 for persons who meditate. Following the same procedure, I get a confidence interval for the non-meditation group ranging from 5.02 to 6.98. Now I'm going to go to the next step, which is turning these into the normal distribution curves. But this time, I'm going to draw both of the curves on the same graph. That means I'm going to use one x-axis on which I'm going to plot two different normal curves, starting with the meditation group. I'll start by drawing my x-axis. Now I'm going to draw the normal curve for the meditation group on this x-axis. I'll center this at a mean of 4 and use my standard deviation to draw my curve. Now I'll draw the lines for my 95% confidence interval, and I'll shade in the corresponding area. And I'll repeat my steps to create my graph for the non-meditation group. When I look at my graphs together, I see a gap between their 95% confidence intervals. This gap tells me that the locations where I'm 95% sure each of their means exist is not overlapping. Therefore, I'm pretty confident that the mean of the meditation group and the mean of the non-meditation group is not in the same location. Therefore, anytime I'm comparing the means of two groups to see if they're significantly different, and I find that there's a gap between their two 95% confidence intervals, I can conclude with confidence that the two means are not in the same location. Now, this is also apparent if I just look at the location of the mean for group 1 and for group 2. Here I can see that those two means, 4 and 6, are not the same number. But remember, I don't trust that 4 is exactly accurate or that 6 is exactly accurate. I believe the means are 4, give or take, the confidence interval, and at 6, give or take the range around the confidence interval. When we compare two means and their 95% confidence intervals don't overlap, our result is considered statistically significant. That's because we're 95% sure that the real population means are not in the same locations. You might have noticed that the gap between our intervals is actually quite small, but that doesn't matter. As long as there is some gap between where one confidence interval ends and the other begins, then our result is considered statistically significant. Try this out on your own from start to finish using the data for groups 1 and 2 below. See if the means of group 1 and group 2 are different enough to be statistically significant. If group 1 has a mean of 20, standard deviation of 3, and sample size of 25, and group 2 has a mean of 26, standard deviation of 3, and sample size of 25. Following the steps, I get a confidence interval for group 1 of 18.824 to 21.176, and a confidence interval for group 2 from 24.824 to 27.176. I then set up my x-axis and plot the graph for group 1, and then I fill in my confidence intervals. Then I plot my graph for group 2 before filling in my 95% confidence intervals. When I do this, it's really clear that there's a gap between the 95% confidence intervals. Even though I see some of the tails overlapping with the confidence intervals of the other graphs, there's a clear gap between the two, telling me that my two 95% confidence intervals are not in the same place. This means that the means of these two groups are statistically significantly different.